And we're trying to find the derivative, I'm assuming? Okay, so we got quotient rule, and then we're gonna have some work to do. So f prime of x, we're gonna take the denominator, 1 minus cosecant x times the derivative of the numerator. The derivative of 1 is 0, the derivative of cosecant is negative cosecant cotangent, good. Minus the numerator, 1 plus, see, denominator times derivative of the numerator minus the numerator times the derivative of the denominator. So the derivative of 1 is again 0. The derivative of a negative cosecant is going to be a positive cosecant x cotangent, cotangent x. That sound okay? All over that denominator squared. 1 minus cosecant x, quantity squared. So the calculus is done, but we're probably going to have to do some simplification here. So we're going to distribute this negative cosecant cotangent times the 1 is negative cosecant x cotangent x. The negative cosecant times the cosecant cotangent times the negative cosecant is a plus cosecant squared x cotangent x. You okay so far? Taylor, we okay? Yeah. Am I going too fast? Okay. And we're going to do a double distribution here, the negative and the cosecant cotangent. So that would be a negative cosecant x cotangent x, and then a negative cosecant squared x cotangent x, still all over 1 minus cosecant x squared. Do we look out and get any cancellation? A little bit, huh? So this negative cosecant squared x cotangent x, and that's positive cosecant squared x cotangent x cancel. The two negative cosecant x cotangent x, can't say that, is going to combine to be a negative 2 cosecant x cotangent x, still over that 1 minus cosecant x squared. No, I don't think we can do anything more with that. Or did they do more? No, that's not an identity. I was thinking that was an identity, but it's not. I don't think. That's about it. Does that match their answer? Yes. What else?
Can we do 61?
61. Do you know what that is?
Yeah, it's secant t over t.
Like this?
Yeah.
And we're going to find this derivative.
Yeah.
So another quotient rule. So we're going to take denominator times the derivative of secant is secant t tangent t. It's denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is just 1, all over the denominator squared. I don't see that really going anywhere. I mean, we could factor out a secant t, but it's not going to lead to any simplification or canceling or any of that, so I don't think it serves really any purpose. So I would just stop there and call it good. Anybody else? Yeah.
63.
You know what that is?
Yes, sir. So x to the 1/2 plus 1/4 sine 2x and then squared on the outside of the bracket.
Here?
Yes, sir.
Like right there?
Yes, sir.
It's a weird place to put that. It wasn't over the end.
No, sir.
No, was this whole thing squared?
No, sir.
Yeah, that was right. That's what it said.
That's an odd way to put that. Because now the question is, how do you interpret this 2x to the second? Because I think I would interpret that as being, this being 4x squared. So I don't think this is very good notation. So I would interpret this as being 1/4 sine of 4x squared.
Okay.
Okay, so we do that, then its derivative, negative 1/2 x to the negative 1/2, plus we got the constant 1/4 that's just hanging out, Now this is a chain rule derivative. So the derivative of sine is cosine. Leave that 4x squared as it is. Then times the derivative of 4x squared, which is going to be 8x. Okay. So I think this 1/4 and that 8 can cancel. So we can call that 2x cosine of 4x squared. And I don't see anything really great happening with that. I'm curious, what is the answer that comes with that? Does it say? Does it look like that, or does it look very different?
I'm not sure, I didn't write it
Okay.
down.
Does anybody have that with them, or no? You must be right. I'm off the hook. Okay, other questions? Okay, so what I want to do a couple practice problems here. One's kind of involved. Let's see what we can do with it. So let's say we have f of x equals 12x to the second minus 2x to the fourth. And so what I would like to know is, first of all, on what intervals is f increasing, and on what intervals is f decreasing. And I would also like to know on what intervals is f going to be concave up and concave down. Is f concave up, concave down. Does the question make sense? How do we answer the question on increasing, decreasing? What do we have to do?
Like equal, like less than or equal to.
What's going to have to, what are we going to look to see as less?
You include, oh,
Pardon me?
I was talking about, never mind.
Okay. I think you're on the right track. But what do we have to know is, we're trying to find where is it positive, where is it negative, what? What tells us increasing, decreasing? The derivative. So we're going to differentiate this, find out where it's equal to 0. This is kind of going back to your AP prep days a little bit. We're going to do a number line thing and then see where on those intervals is it going to be positive or negative. And where the first derivative is positive, that's where we're going to get that the function is increasing. And where the first derivative is negative, that's going to tell us where the original function is decreasing. Does it make sense that what we're doing in y? Okay, so the derivative, f prime of x, is going to be what? 24x minus 8x to the third. So we want to set that equal to 0, and we're going to find out where is the derivative equal to 0. Okay, now, well, let's see. We got a common factor of what? 8x. And that's going to leave behind
3 minus x squared.
3 minus x squared. So if this is equal to 0, then x could be 0. And we need to know where is 3 minus x squared equal to 0. That's going to be when x is, nice, positive or negative square root of 3, plus or minus square root of 3. Now, we haven't really talked about these too much yet. Abby, you with me? Okay, so these we are going to give a name. We're not really ready for that yet, but we'll call it. These are going to be known as critical points, which we will abbreviate, because we abbreviate everything in calculus, as CPs, so critical points. So these are going to be where our derivative is 0. And also if we had somewhere where the derivative was undefined, that would also qualify as a critical point. So I'm going to put those down here. Now we're flashing back to our AP prep days where we were doing like domain questions. And we want to know where is this positive, where is it negative. So these are the places I have marked here are where the derivative is 0, and those are places where it could change from positive to negative or negative to positive. Okay, but everywhere in this interval, if I pick any of those intervals, that's going to all be the same sign. The derivative is not changing sign between here because it's nice and continuous and it couldn't hop over from positive to negative without crossing through 0. So let's see, square root of 3 is a little bit less than square root of 4, which is 2. So if I put maybe a negative 2 into, I'm going to plug it right in here. So negative 2 would make 8 times x negative. Negative 2 squared would be 4. 3 minus 4 would be negative. A negative times a negative would be positive. So to the left of negative square root of 3, this derivative is going to be positive. Squirrel. Never mind. In between 0 and square root of 3. Well, 1 is in between 0 and square root of 3. So negative 1 is in between negative square root of 3 and 0. So we plug in a negative 1. Well, the 8x is still going to be negative. Negative 1 squared is positive 1. 3 minus positive 1 is, which is a positive. And a negative times a positive is negative. So this is now changed to a negative first derivative. You with me? Boy, sometimes it feels like I'm all alone here. Plug in a positive 1 on this side. Now the 8x is going to be positive. 1 squared is 1, 3 minus 1 is still 2, still positive. Positive times positive is positive. Something to the right, maybe a positive 2. This will be positive, but now 2 squared is 4, 3 minus 4 is, so now we're back to a positive times a negative, it's going to be negative. Okay, so we can see from here, this sign chart, we'll call this, we can see where the derivative is positive and where the derivative is negative. Now, we can then answer the question. We'll say f is increasing on those intervals where our derivative is positive, but with a slight difference. So right at the boundary point is where the derivative is 0. But when we're asked where is f increasing, as long as f, the original function, is defined there, that's going to be included in the interval where it's increasing and also included in the interval where it's decreasing. Okay, so f is positive, f prime is positive for x strictly less than negative square root of 3, but f is increasing for x less than or equal to negative square root of 3. So you can either write it using your interval notation, inequality notation, or you could write it using your interval notation if you like that better. Either is equally acceptable. Okay? It's also increasing in between 0 and square root of 3, and we're going to include the 0 and the square root of 3. So I'm going to destroy some of this hard work that I just did. That's okay. Oh, I didn't want to destroy the derivative. Oh well, too late now. So negative square root of 3 less than or equal to 0, sorry. 0 less than or equal to x less than or equal to positive square root of 3. That's where this function is increasing. Good to go? Any nods of heads? Okay. And then f is decreasing on the intervals where the derivative is negative. We're going to include the endpoints. So that's going to be from negative square root of 3 less than or equal to x less than or equal to 0, also for x greater than or equal to square root of 3. I'm going to reconstitute my derivative here. I don't remember what color I had it in. An idea there. Oh well. F prime of x we said was 24x minus 8x to the third. I'm going to have to build on that here shortly. Okay. Questions so far? So we move on now to the concavity questions. I don't think I need that anymore. Okay. So how do we answer questions about concavity? We look at the second derivative. So the same process we just did with the first derivative. finding it, setting it equal to 0, finding the zeros, the critical points, doing our number line. We're going to do the same process now with the second derivative. So f double prime of x is going to be what? Good. Good. Boy, somebody put some thought into this problem, I think. So now what are we going to do with this? So it's a 0. And how you want to do this? You want to factor? Do you want to just add? Okay. Should we pull out a 24? And there's a couple ways you can go here. Can we factor 1 minus x squared? That was a rhetorical question. Of course we can. What do we get? Nice. 1 minus x, 1 plus x. Okay, so now, where the first derivative is 0, we call those CPs, or critical points. Where the second derivative is 0, we call these the pips. I used to team up with Gladys Knight. That was way before your time. That's for a potential inflection point. Potential inflection point. That is going to be where the second derivative is 0, and that is going to be where? Negative 1 and 1. Thank you. There is somebody else out there. So these are the potential inflection points. We're going to do like we did with the first derivative, but now we're talking about the second derivative. And we're going to again go to negative 1, positive 1. These are places where the second derivative is 0, so possibly the second derivative could change sign there. Maybe not. We'll see. So we'll test the representative from the far left region, negative 2. So plugging it into this factored form, this 24 is always positive. 1 minus a negative 2 is going to be positive. 1 plus a negative 2 is going to be negative. A positive times a negative is negative. A nice representative in the middle region would be 0. 24 is always positive. 1 minus 0 is still positive. And now 1 plus 0 is also positive. Product of 3 positives is positive, so we're positive in the middle. And far right's like 2. Now 1 minus 2 is going to be negative. The others remain positive. The product of 2 positives and a negative is going to be negative. So knowing the sign of the second derivative allows us to answer the questions about where is f concave up and where is f concave down. So it will be concave up on the intervals where the second derivative is positive. On intervals for concavity, we never include the endpoints, so it's going to be from negative 1 less than x less than positive 1. And where it's going to be concave down is where the second derivative is going to be negative. So that's going to be x strictly less than negative 1 or x strictly greater than positive 1. Questions on it? Oh, soon we'll be drawing a graph of that thing. Let's find an equation of a tangent line. Find an equation of a tangent line to f of x equals tangent of pi over 2x at x equals 1/2. And in fact, let's also, just to make it interesting, let's also find, that's part A, and part B, we'll find an equation of the normal line. 2 f of x at x equals 1/2. So what's the difference between a tangent line and a normal line? Yes, a normal line is perpendicular to the tangent. So here we got an x value. To find an equation of a line, what do we need? A y value, so we're going to plug that in. What else do we need? Slope. How are you going to find slope for a tangent line? Derivative. Plug it in, you'll get slope. We'll write it down. And then we'll take that same slope we found here, but to get the normal line, we're going to take the negative reciprocal, but use the same point. Does that make sense? All right, I think we ought to have somebody come to the board. We can have 3 or 4 somebodies at the whiteboard, another one up at the chalkboard. We'll see if we can get volunteers first to volunteer themselves voluntarily before they get volunteered.
Can I come out for school today?
Yeah.
I don't know how well that quick went for me, so I think I simplified them to like the tier car.
Okay, we are getting that f prime of x is going to be secant squared pi over 2x times pi over 2 from the chain rule. When we evaluate that at 1/2, we're going to get pi over 2 times 1 over cosine squared of pi over 4. And that is going to turn out to be just pi. That is going to be our slope. When we plug this in, the tangent of pi over 4 is 1. So we have y minus 1 is